Hi, I'm Lauren White. In this lesson, we'll talk together about how to evaluate the stereochemistry of the product of an SN1 reaction. So SN1 reactions are interesting because the products of them can be a racemic mixture. And remember, a racemic mixture just means equal portions of the R configuration and the S configuration. This is not always the case, though. We don't always get a racemic mixture, but it is a possibility. Why? Well, let's think about the shape of molecules for a bit. Our reactant will be a carbon attached to 4 substituents, which is sp3 hybridization, which means we get this tetrahedral shape to our molecule. However, once our leaving group leaves, our carbon is now only bound to 3 things. And so now it's sp2 hybridized. So what does that mean for the shape of the molecule? Well, it's planar. This molecule, our carbocation, is laying flat on your screen. This is the key to why we can get racemic mixtures as our products. Okay, imagine this molecule is your friend and they're floating flat on the surface of a pool. Since he's floating around flat, if you wanted to play a prank and scare him, you have 2 options. You can attack him from above the water. You can, throw a ball or jump on him, or you could swim under the water and attack from below. The nucleophile in an SN1 reaction has that same option. It can attack from either side. So you can imagine our nucleophile could come around from the back, or it could come from the front. Because of this, we can get 2 products, one with an R configuration and one with an S configuration. Now remember that a racemic mixture is not optically active. Since the 2 isomers, R and S, are present in equal amounts, they kind of cancel each other out, and overall there is no net rotation of light. Also, keep in mind that it doesn't matter if our reactant has a chiral center or not. Since the carbocation will be planar, the nucleophile can always attack from either side, and it could introduce chirality to the product and create this racemic mixture. Let's look at some examples to demonstrate this. This question is asking us for the chirality of both the reactant and the product. Let's start with A. We want to look at the reactant first. Remember, for us to have a chiral carbon, we must have a carbon bound to 4 distinct or different groups. So here we have this central carbon attached to 3 methyl groups. And since 3 of those substituents are the same, this reactant is achiral. Well, what about the product? Well, same thing. We have a central carbon connected to 3 methyl groups. 3 substituents are the same, so our product is also achiral. So here we had an example where we never had any chirality, and that's perfectly fine for an SN1 reaction. This just demonstrates that having a racemic mixture or stereoisomer at all as a product of an SN1 reaction is a possibility, not a necessity. All right, let's try B. Reactants first. The first thing I notice is that I only see 3 substituents around my carbon that's attached to the leaving group. Now remember, we do have an implied hydrogen here, but where is it? Well, we don't know given this diagram. Notice how this diagram is different from the one given to us in the products. We don't have any wedges, we don't have any dashes. And remember, those wedges and dashes are what tells us if the atoms are coming out of the page or going into the page. So that's what we need to determine the chirality of this reactant. Basically, we need to be given diagrams like these, for instance. Notice now in the molecule on the left, we have a wedge showing the OH coming out of the page and a dash showing the H going into the page. On the right, we have a wedge showing the hydrogen coming out of the page and a dash showing the OH going into the page. So you know, the one on the left here is R and the one on the right is S. But remember, we weren't given either of these diagrams in the question. So all we can say for sure about this molecule given to us in the question is that it definitely has a chiral center, and so it must be either R or S. Either way, our leaving group is going to leave, and we'll get our carbocation shown here. And our carbocation is planar. Remember, it's flat against your screen. As usual with an SN1 reaction, our nucleophile, the chlorine, could come from the back or it could come in from the front. And we get these products. Let's start with the one on the top. Remember, we do have an implied hydrogen again, but this time we know that it's going into the page since our chlorine is coming out of the page. And let's number our substituents. Chlorine is first, propyl is second, methyl's third, and our hydrogen is fourth. Again, we can draw our circle. It is clockwise, which is R. Our hydrogen is going into the page, so we don't need to switch. The designation of this molecule is R. Now let's look at the bottom. Here, our chlorine is going into the page, so we know that our hydrogen must be coming out of the page. Again, we can number our substituents. They haven't changed though. Chlorine is 1, propyl's 2, methyl's 3, and hydrogen is 4. We draw our circle. It's clockwise, which is R, but our lowest priority group is coming out of the page, so we switch it and we get S as the designation for this molecule. So in this reaction, we have a chiral reactant that produced chiral products in equal amounts. So we do have a racemic mixture here. Let's do one more. All right, reactants first, of course. On our central carbon, we have 4 different substituents, but none of them are hydrogen. So let's just number them all and figure out which one is the lowest priority. Iodine will be our highest priority because it has the highest atomic weight, then oxygen, then a propyl group, and then our ethyl group. Let's draw our circle going over our lowest priority group, and this is going counterclockwise. So we would temporarily say S, and then we check the ethyl, and we see that it's coming out of the page. So we need to switch our designation to get that this is R. Now let's look at the products. The carbon our nucleophile attacked certainly has 4 bonds again, but notice that this substituent on the top and the substituent on the bottom are the same. Since we don't have 4 distinct substituents, this molecule is achiral. So here we had a chiral reactant give an achiral product. Now, you should feel more comfortable evaluating the stereochemistry of an SN1 reaction product.